All right, today we're cracking a code, a really big one. We're going to see how one of science's greatest achievements explains, well, pretty much everything. So let's start with a really basic question, something you've probably wondered about. Why do atoms even stick together? Why do two hydrogens and an oxygen get together to make water? Or what's the deal with sodium and chlorine hooking up to make the salt on your fries? What is this invisible glue that holds our entire universe together? Well, that glue actually has a name. It's a chemical bond. It's the physical process that pulls atoms together and holds them tight. And what's their motivation? It's all about stability. See, atoms are always looking for a more stable, more comfortable state. And for them, forming a bond is the easiest way to get there. Okay, so how can we possibly predict which atoms are going to get together and how they'll do it? Well, for that, we need the ultimate cheat sheet. And this is it. The periodic table of the elements. I know, it might look a little intimidating, but trust me, it's not just a poster for your high school science class. This thing is a master code book. It's a map to all the building blocks of the universe, and it's laid out in this brilliant way that just reveals all their secrets. And reading this map is actually pretty straightforward. You just need to get two main ideas. The vertical columns, those are called groups. You can think of elements in the same group, like lithium and sodium, as being part of the same family. They have really similar personalities. The horizontal rows are called periods. As you move across a period, you see properties change in a very gradual, predictable way. Right, but it's within that structure, those groups and periods, that things get really interesting. That's where we start to decode the hidden patterns. Just look at this. The way the table is organized reveals these incredible, predictable patterns, or trends, as scientists call them. As you go across a row or down a column, properties like an atom's size or how much energy it takes to pluck off an electron, they change in these really consistent ways. And that is the key. These patterns let us predict how an element is going to behave. Now, out of all these different trends, there is one master clue that is absolutely key to understanding bonding, and that is electronegativity. It's basically a measure of how badly an atom wants to grab onto electrons. You can almost think of it like an atom's personality. Is it a generous giver, a greedy taker, or is it more of a team player, happy to share? The answer to that question tells us pretty much everything we need to know. So, okay, we've got our code book, the table, and we've got our master clue, electronegativity. Now we can finally crack this case. And it turns out atoms solve their bonding problem in three main ways, which I kind of like to think of as sharing, stealing, and swimming. Okay, first up, sharing. This is what we call a covalent bond. This is what happens when two atoms both want electrons about the same amount. They have similar electronegativity. It's like a tug of war where neither side can win. So what do? They compromise. They agree to share a couple of electrons, and by doing that, they both get to be more stable. And this is a perfect example. Look at hydrogen chloride. Hydrogen needs one more electron to feel complete, and hey, so does chlorine. But neither one is powerful enough to just rip an electron off the other, so they work it out. They share a pair. Boom, everybody's happy. But what happens when it's not an even match? That brings us to our second strategy, stealing. This is the ionic bond. Here, you've got a massive difference in electronegativity. One atom wants an electron so bad, and the other one, well, it's not holding on to its own very tightly. So instead of sharing, one atom just straight up steals an electron from the other. The classic case here is regular old table salt, sodium chloride. Chlorine is a total electron hog. It's super electronegative. Sodium, on the other hand, has this one extra electron that it's just not that attached to. So chlorine just yoinks it. And in that moment, chlorine becomes negatively charged, sodium becomes positively charged. And you know what they say? Opposites attract. Bam, you've got yourself an ionic bond. All right, our third and final strategy is the metallic bond. And this is what happens in, you guessed it, metals. And it's a totally different ballgame. Instead of a one-on-one thing, you get this whole crowd of metal atoms together, and they all kind of agree to just give up their outermost electrons into this big shared community pool. And what you end up with is this awesome situation that scientists call a sea of delocalized electrons. You've got all these positive metal cores just kind of floating or swimming in this shared sea of negative electrons. It's this collective sharing that holds the whole chunk of metal together. Okay, so let's recap. We've got sharing, stealing, and swimming. But so what? Why does any of this matter? Well, it matters because these different bonding strategies explain the properties of pretty much everything in the world around us. Let's see how these bonds literally build our world. Okay, think back to that ionic bond in salt, that super strong attraction between the positive sodium and the negative chloride. It forces them to line up in this perfect, rigid crystal structure. That's why salt is a hard, brittle little crystal. And it's also why it has such a crazy high melting point. You need a ton of energy to break up that powerful attraction. And what about that sea of electrons we saw in metals? Well, because those electrons are totally free to zip around wherever they want, they're amazing at carrying an electrical current and moving heat around. This is exactly why metals are conductive. And that free-flowing sea of electrons, it's also what reflects light in a way that gives metals that characteristic shine. So let's just pull this all together for a second. This chart gives us a fantastic side-by-side look. Covalent bonds, that's all about sharing. It leads to stuff with low melting points that don't conduct electricity. Ionic bonds, that's the transfer, the stealing. You get these brittle, high melting point crystals that only conduct electricity when you dissolve them. And finally, metallic bonds, with that awesome sea of electrons, give us those conductive, shiny materials we know so well. So when you think about it, from the water you drink, to the rocks under your feet, to the metals inside your phone, the patterns in the periodic table give us this incredible power to predict how atoms are going to connect. We've seen how it explains the very nature of matter. Which leads to the big question, right? If it can predict all of this, what else about our universe can its patterns help us predict?